So we are going to talk about number one, some exceptions to the configuration that we've seen. Basically, situation to situation, some situations arise in which the normal pattern doesn't apply, it doesn't work, and there is a better alternative available. Because remember, low energy is more stability, and this idea of stability, we will continue to work with it, refer to it. It simply means, does the thing retain the way it is? A stable molecule remains the way it is, and unstable changes that. So, for example, carbon dioxide will remain as carbon dioxide in fairly large range of temperature, pH, or dissolved in stuff and all that. Carbon dioxide stays the way it is, but carbon monoxide doesn't. Carbon monoxide is pretty much unstable because the moment it gets a chance, it's going to bind to something and break and change its form, change its shape, change its structure. So that is why we say that carbon monoxide is relatively unstable and carbon dioxide is more stable because it remains the way it is. And this idea of stability will carry forward to the rest of your A levels, that things remain the way they are, which means they're more stable. One thing that always leads to better stability is lower energy. So if something has low energy, there is likelihood that it will remain the way it is and it will retain its shape, its current structure. So for example, if you talk about electronic configuration of zinc, then zinc is going to remain as 4s2 unless you give it an option to change that. And 4s2, the two electrons are going to leave. And once they are lost, once they are given away, zinc will remain the way it is. Zinc will remain as 3d10 without trying to adjust that a little bit. But there are elements that don't do that. There are elements that form one form and then they try to form another one. And we won't get into much details, but there is one that I need to talk about, which is copper. So if you look at copper, copper has 29 electrons. Let me break it down. So the 29 electrons, the first 18 are obviously going to be arranged just like argon. And now you have 18 gone, you have 11 more to adjust. Copper has the fourth shell available for S. So the next two go into 4s2. Okay. So it goes and fills that up. So there is 4s2, 1, 2, done. And then there is 3d, which is available. And you know that 3d has low energy than 4s. So that is why 4s is filled. 3d has high energy than 4s. So it is 4s is filled first. But the moment it is filled, it changes that, and the next electrons are going to go into 3d now. 4s is now at a higher energy level once it's filled up. So the next next 9 are going to go in there, and that is what happens. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and we would expect 3d 9. That is what we would expect, right? But here's what happens. Copper would be in much better position if this last orbital was filled up. Because right now, remember, 4s is at a higher level. So before they bond, before they're filled up, 4s is here, 3d is here. 4s is at a lower energy. This is energy going up. But the moment it's filled, 4s goes to a higher level and 3d is there. And now there are 9 electrons there. There is a chance that this one electron might want to jump back, because not only is 3d at a lower level, if an electron were to come in here, and if an electron were to come in here in place of the 5th orbital in 3d, this completes not just the 3d orbital, this actually completes the whole 3d shell, a third shell, which obviously fills this, and the electron is stabilized. The configuration is stabilized. Not just that, this 3D cloud right now, the way these electrons are arranged, these orbitals carry some space around them. So you know that this has this form. These are the shapes of PD. You know that these forms have these electrons in them. So electron cloud is not symmetrical at the moment. Kyun? Because there is one orbital that is completely filled up. One electron is repelling the other electron, opposite spins, balancing each other's effects. But there is one in there जिसका balance नहीं हो रहा effect क्योंकि उसके oppose करने वाला कोई है नहीं. So for all these factors, and obviously अगर आपने सिर्फ याद रखना है कि अच्छा ये क्यों होता है, so the easiest explanation is that now the electron from 4s is at a high energy level and 3d is at lower energy level. So the electron simply moves from here and comes here. Now the configuration is not 3d9 and 4s2. The configuration is argon, the first 18 electrons, 3d10, 4s1, and that is pretty stable. Okay, but remember, this electron has been brought back. Okay, so this happens when the atom has to then lose some energy. So to bring an electron back from a high level, it has to lose that energy, but it does that. It takes a compromise, and that compromise helps it become more stable, helps it attain a better, the electron cloud is more symmetric, and it has these advantages कि ये इसको prefer करता है. So copper is an exception to the normal way we do it, the configuration. Copper में हमारे पास this electron is going to come back to a lower level. And chromium also does this. So if you look at chromium, then chromium is, so chromium has 24 electrons. And these 24 electrons are going to be arranged like the first 18, obviously, like argon. And then you have 6 more to go. So you have 3D and you have 4s. So the next 2 go into this. And then you have total 6, 4 left. So 1, 2, 3, 4. And just like that, the electronic cloud is also not stable right now because 3D has 5 orbitals. One of them is empty and 4 of them are not empty. They're filled, half filled. So again, there is an option that one electron from 4s can come back, and it will come back from here over here. So वो यहाँ आएगा, उसका spin आप opposite करना चाहते हो, अब इसको opposite लिख देते हो. Usually we just write it like that. So there you go. So now instead of having, which we would normally expect chromium to be 3d4 and 4s2. That doesn't happen. Instead, chromium makes argon and then 3d5, 4s1. Based on this, what configuration or what charge would we expect chromium to be? Yeah?
4s1 वाला नहीं पीछे आ सकता.
What do you mean पीछे नहीं आ सकता?
सर यानी अब 4s में अब सिर्फ एक ही इलेक्ट्रॉन है, वो भी पीछे 3d में आ जाए.
नहीं, देखो, if that comes in here, it will experience some electron pair repulsion because right now they're all individual ones, but the moment it tries to pair up, there will be some repulsion. यहाँ पे उसके पास वो repulsion नहीं है. There is no repulsion here. ठीक है, इसको हम कहते हैं Hund's rule of maximum multiplicity. ठीक है, so what happens is that Hund's rule की वजह से they try to avoid pairing up again because it has that extra repulsion. So abhi wo aise stable hai, stays the way it is. And obviously when you're removing electrons now, copper will give 1 electron and make copper +1, and so will chromium. Chromium bhi +1 banata hai, which is usually what many transition metals don't do. Most transition metals just make 4s2, और वो इसी वजह से होता है कि उनके पास 4s2 होते हैं, तो 2 इलेक्ट्रॉन लूज करके वो +2 का चार्ज ले लेते हैं. But copper and chromium are special cases which are able to gain +1 charge or +2 charge, and all because copper and chromium have a 4s1. Okay, so this configuration helps you understand that maximum stability is what they're after. They're not after some patterns. These patterns are there because we have found them there. We have found them in ionization energy. और ये हमारा मॉडल काम करता है. But यही मॉडल हमें ये भी बताता है कि things will change. Things are very flexible if they are able to get their end goal. And end goal क्या है कि उनको इलेक्ट्रॉन क्लाउड को स्टेबल करना है, सिमेट्रिक करना है, और ओवरऑल स्टेबिलिटी अचीव करनी है लोएस्ट एनर्जी लेवल पे. वो एंड गोल उनका अचीव हो रहा है तो वो 4s पे इलेक्ट्रॉन नहीं रखते, वो उसको वापस पीछे बुला देते हैं. एंड व्हेन यू आर रिमूविंग इलेक्ट्रॉन, दैट डज द सेम थिंग. सो कॉपर विल रिमूव द 4s and give us copper +1 charge, or chromium will do the same, +1 copper. Chromium भी हमें मिलता है. But you can notice that iron वगैरह, they don't give +1. Iron आपको, if you take the example of iron, then iron gives us
+2 कैसे देता है?
+2 इस तरह से देता है because iron is 26 electrons.
No sir,
So
I mean how does copper give +2?
Oh, +2 because that extra electron that it has brought back, it can lose that as well. जो उसने वापस लेके आया ना, मतलब वो इसको यहाँ लेके आया था, वो इसी को यहाँ से उड़ा दे. So now it has lost both those 4s2. So इसको वो जो एक्स्ट्रा एनर्जी लूज करनी पड़ी थी वो भी नहीं करनी पड़ी. Remember that when it brought this from here to here, it has to lose some energy. वो भी उसे नहीं करनी पड़ी, उसके दोनों electrons lose हो गए. So that's how it gives us +2.
So I don't understand how it can lose 2. Like the second one that it brought back, how can it lose that?
So basically, when copper is the way it is as an element, copper has to fill them up like this. And now 4s is at a higher level. If copper is not able to bond with something, then copper has two options. Now I'm going a little beyond AS. If copper is not able to bond with something, copper has two options. One option is which copper does if you have large number of copper atoms available. If you have large number of copper atoms available, copper will lose those two, make copper lattice, जिसको metallic bonding कहते हैं. ठीक है? But if it doesn't have that option, let's suppose copper is gaseous, हर atom individual है या बहुत ज़्यादा copper atom available नहीं है, then what copper tries to do is copper शुरू में इसको एक पीछे ले आता है और इसको इस तरह से रख लेता है. So अगर तो free electrons वो दे सकता है, कोई electricity flow करनी है या कुछ करना है इस तरह से, it loses both of them. If not, it brings one back and becomes a stable cation by losing this +1 charge. And the third option is कि वो इसको भी lose कर दे और इसको भी lose कर दे, and that's how it forms copper +2. It will try to that because now उसको देखो, all of this is a compromise. Bringing the electron back is a compromise. ठीक है? इलेक्ट्रॉन पहले उसने एनर्जी गेन की थी, उसको ऊपर लेके गया था, फिर वापस लेके आया. वो एक्स्ट्रा काम क्यों कर रहा है? क्योंकि उसके पास कोई और ऑप्शन नहीं. जब उसके पास ऑप्शन होगी ना कि कोई चीज उससे इलेक्ट्रॉन ले रही है, वो इन दोनों को लूज करेगा और वो +2 आयन बन जाएगा. और +2 से ज्यादा फिर वो नहीं जाना पसंद करता, बिकॉज +2 पे उसका 3D भी 4s जो है वो खत्म हो गया, उसको कोई कॉम्प्रोमाइज नहीं करना पड़ा, इजी लाइफ. सो आई वाज टॉकिंग अबाउट आयरन. सो आयरन व्हाट इट डज इज दैट आयरन हैज 8 इलेक्ट्रॉन्स टू गो, so it's going to fill 4s2, and after that 3d6. And now here's the thing, if I were to draw it, obviously 4s से पहले fill होना है, and this is how it goes. So iron immediately when it gets a chance forms +2, because +2 per it's going to lose 4s2, these two electrons gone. But then if it loses this extra one, this one which had some repulsion, mutual pair repulsion coming out, this electron, if it loses that as well, it's going to try to do that, and 3d5 बन जाएगा. Now the cloud is symmetric because every orbital is half filled, so that is why it becomes iron 3. So iron 3 is what it prefers, and the higher the oxidation state, higher the energy requirement is. So iron 3 पे जाके ये रुक जाता है, क्योंकि इसको इससे ज्यादा करने की ऐसा जरूरत नहीं है. Sure, there are ways to get iron +5 and iron +8 as well, लेकिन वो बहुत unstable होते हैं. इस वजह से ये situation it's the best one so far. Okay, we have talked about the configuration, so that is how it doesn't really follow that. But there is another thing that we need to talk about before we get to the next chapter, and that is the shape of the orbitals. You know that shape of the orbital is like this. S is this one, P is this one, and this is S is all the way. So this is PA, PY. Electrons are going to reside in there, right? And electrons are going to repel each other. And they will try to obviously cover a lot of this in the same region. So for example, if you, on your laptops or mobiles, whatever you're using, go to this website, ptable.com, okay? And in there is a link for electrons. So select hydrogen. You will see that I can share screen for that. So if I select hydrogen here, then you can see that hydrogen has this what you call red color ka. It has this thing you can see that is red 1s orbital. The moment I go to lithium, what happens? Do you see that small red in there? That is 1s, and this blue one around it, that is 2s. So you can clearly see how big 2s is compared to 1s, and how far the electrons can come from the nucleus. Now, one important thing, electrons do not actually move on the surface of this. ऐसा नहीं कि sphere और इसकी surface पे वो घूम रहे हैं. They can be anywhere inside the surface. They can be anywhere in the sphere. So this sphere is more like a boundary. कि यहाँ पर उसके मिलने का चांस ज्यादा है. This is the higher chance of identifying or finding that electron inside. But right now, it can be anywhere in there. So if I were to define what an orbital is, I will say that orbital is a region of space where there is a high chance of finding an electron. And if I were to define the shape and the surface of the shape, then I will say it is the surface of the shape is where there is a maximum 5 beryllium, then modular tree as the 2s1. But the moment I select boron, now this is only showing the outermost one, it's not showing the inner one. Because inner वाला उसके अंदर है, but P उससे बहुत बड़ा है. ठीक है? So P उसके अंदर मौजूद है कहीं पे. ठीक है? Now if I select carbon, it is showing me PZ, and if I select nitrogen, it is showing me PX. So boron में PX था, carbon में outermost PZ था, now P all that. And then we have oxygen. Oxygen में वापस वही आ गया है जो कि overlap की वजह से होया था. You can see that PX and PZ are the ones. Color वो ऊपर नीचे सिर्फ आपको identify आसानी से करने के लिए करता है. Fluorine has the outermost as PZ, just like carbon, and neon has the PX1 again or PY1 again, ताकि वो overlap उस तरह से show कर दे. Now let me go to 3S. There you go. Whoa, so much bigger. Do you notice that blue sphere in the middle? ये बिल्कुल देख रहे हैं? That blue sphere is 2s. जो lithium में हमें outermost नजर आ रहा था, sodium में that is the 2s1, and magnesium में भी obviously यही है. And let me select aluminium, and here you go. This is much bigger. अगर मैं इसको zoom in करूं तो मुझे यहाँ पे वो छोटे से नजर आ रहे हैं 2s और 2p वाले. Do you notice them? That deep inside the small thing. That is how bigger these orbitals are compared to this. Similarly, if I move on to potassium, then वो आपके सामने है कि वो छोटा सा 1s, उसके बाद 2s, then 3s, then 4s. So these shells are these orbitals are becoming bigger and bigger. An orbital is the physical space where the electron is. In scandium, you can see this, the Z1. Okay, sorry, the d orbital. टाइटेनियम में ये है, वेनेडियम में ये है. आपके सामने उसकी शेप्स है, मैंने आपको बताया था ये लोब सी शेप है उसकी, और ये उसकी बटरफ्लाई शेप है, ऊपर से आप देख सकते हो. Anyways, you can go to this website and play with that. Now there's a fundamental problem with all of this. If you look at P, then if an electron wants to stay in P, then it has to be 90 degrees from the other P. That's a problem. Why is that a problem? Because when they try to bond, the other electrons and these electrons will actually be confined closer to each other, और बहुत ज़्यादा problem हो जाएगी. Secondly, what option does an atom have अगर उसके पास एक ऑर्बिटल में एक ही इलेक्ट्रॉन, वो इलेक्ट्रॉन जो है उसके स्पिन को कैंसिल आउट करने के लिए कोई चीज है ही नहीं. इट वांट्स टू स्टेबलाइज दैट, एंड टू स्टेबलाइज दैट व्हाट डज इट नीड? इट नीड्स सम अदर इलेक्ट्रॉन ऑफ द ऑपोजिट स्पिन टू कम इन एंड स्टेबलाइज इट. तो वो ये नहीं कर पाते इंडिविजुअली. एक इलेक्ट्रॉन इस पी के अंदर घूमता रहेगा, वो दूसरे इलेक्ट्रॉन्स को रिपेल करेगा, 90 डिग्री के एंगल पे होगा, मुश्किल हो जाएगा. सो व्हाट हैपेंस देन? व्हेन दे बॉन्ड, they give up on these shape. They can't retain this shape, and what happens is that when they want to bond, problem is one atom has one orbital which is filled, and the other one also has one orbital that is half filled. दोनों में एक एक इलेक्ट्रॉन है. I'll take the example of hydrogen. हाइड्रोजन एक ऑर्बिटल है, इसमें भी एक ऑर्बिटल है. अब ये दोनों आपस में जब बॉन्डिंग करना चाहते हैं, दूसरा हाइड्रोजन भी है, तो वो चाहते हैं कि अच्छा इंडिविजुअली आवर स्पिन इज नॉट बीइंग स्टेबलाइज्ड, बट टुगेदर इफ वी वर टू कंबाइन दीज टू इलेक्ट्रॉन्स, दैट स्पिन कैन बी कैंसल्ड आउट, द इफेक्ट कैन बी कैंसल्ड आउट, एंड फॉर दैट they try to overlap these two orbitals. The word is overlap. So one hydrogen with its sphere and the other hydrogen with its sphere, they try to overlap. इसका ये जो इलेक्ट्रॉन है इधर वाला इलेक्ट्रॉन, सॉरी ये वाला इलेक्ट्रॉन गॉड इधर, and when that happens they form a new orbital which has one hydrogen electron from one hydrogen and the other electron from the other one, and they're both cancelling each other's spin. But now here's a problem. हाइड्रोजन का एक s था, तो जब इंडिविजुअल था तो उस s के अंदर इलेक्ट्रॉन कहीं पे भी घूम रहा था. But now, because of the sharing, this electron has been confined to just this region. अब वो इलेक्ट्रॉन उसके अंदर तो कहीं पे भी घूम सकता है, लेकिन अगर वो ज्यादा दूर जाने की कोशिश करता है, so the other nucleus pulls back on it. And what happens is that now hydrogen is not actually moving all around this hydrogen atom, the electron. The electron is just within the region in between these two nucleus. And this is a new region of space where this electron can be. Pehle, it could have been anywhere inside this region of space, the S. But now that's not the case. दोनों इलेक्ट्रॉन्स इस नए क्लाउड के अंदर रह सकते हैं. यहां पे वो जहां मर्जी, but they can't further away because the hydrogen nucleus is going to pull back on them. And this new orbital is called sigma. Usually, for some reason, people call it sigma orbital. Oh, sorry, sigma bond. But I want to clarify that this is not sigma bond. This is just sigma orbital, जिसको हम bond कह देते हैं, क्योंकि होता तो ये bond के बाद ही बनता है ना. Now there is a problem with this one. Bigger problem is कि अभी S की shape थी spherical, इसकी shape अब spherical नहीं रही, इसकी shape change हो गई है. This is more like, but this one is easy. What about HCl? If I look at the electron of hydrogen, वो ऐसे है in 1s. But if I look at chlorine, तो chlorine का last सिर्फ मैं आपको दिखा रहा हूँ. Last one is over here. That is P. अगर मैं इलेक्ट्रॉन की शेप को देखूं, the orbital की shape, hydrogen's orbital is like this, but chlorine's last orbital is probably like this, जिसमें एक इलेक्ट्रॉन घूम रहा है. So when they try to overlap, when they try to come close to each other, तो ये ऐसे आएगा, तो इसकी shape बदल जाएगी. Now they want to share electron, and that means the electron has to stay somewhere in between these two. And so they also form a sigma between H and between Cl. And this sigma has slight confront, थोड़ा सा ना इसका एक side में tail निकली होगी. This is also sigma. This is also a sigma orbital. Similarly, if a chlorine wants to bond with another chlorine, then chlorine का last वाला ऐसे है, दूसरे chlorine का भी last वाला ऐसे है. When they want to overlap, the electron is confined to the region between the two nucleuses, and that is why nuclei or nucleuses, you get another sigma. इसमें थोड़ी सी tail दोनों sides पे होगी, which means आसानी के लिए sigma equals first or single bond. First bond भी कह सकते हैं. What about double bonds? Let's suppose oxygen है, O2 बनाना है हमने. ऑक्सीजन का भी P में ही है दोनों. एक ओवरलैप ऐसे हो जाएगा, दूसरे का भी ओवरलैप ऐसे हो जाएगा. दोनों आएंगे, ओवरलैप करेंगे, ये चीज दोबारा बन जाएगी. P बन गया, इलेक्ट्रॉन इन दोनों के बीच में घूम रहा है. बट व्हाट अबाउट द सेकंड बॉन्ड? सेकंड वाला तो हमारे पास ऐसे था, ये ऑक्सीजन है, दूसरा भी ये ऑक्सीजन. अब इनको अगर मैं क्लोज लेके आता हूँ एक दूसरे के, तो ये ओवरलैप इस तरह का बहुत क्लोज करके करना पड़ेगा. और इसमें एक और प्रॉब्लम है, ऑलरेडी सिग्मा बॉन्ड बना चुके हैं, ऑलरेडी ये बीच वाला एरिया कवर्ड हो चुका है, तो ओवरलैप कैसे होएगा? ओवरलैप विल बी इस वाले का इसके साथ, इस वाले का इसके साथ. So the overlap is going to be like this, kind of like, let me try to draw it again. आपके पास ये ऐसे था ना, अब ये इधर को ओवरलैप कर रहा है, इधर को ओवरलैप कर रहा है, इधर को ओवरलैप कर रहा है, इधर को ओवरलैप कर रहा है. And when they try to overlap, so what happens? हमारे पास, तो when they try to overlap, you get something like ये इधर से ऐसे होएगा, इधर से ऐसे होएगा, which basically means that you're going to, if I have a neat diagram, you will get a cloud that looks like this, above and below. So above and down below. ये क्या लिख रहा हूँ? This is from a novel. Yeah, so basically now the electron cloud is ऊपर को, not नीचे को, क्योंकि ये सिग्मा है. सिग्मा में इलेक्ट्रॉन्स पहले से मौजूद हैं, वो इनको आने नहीं देंगे अपनी जगह पे, रिपेल करेंगे, which means you have what we call pi cloud, a pi orbital, which is always coming from the second or third bond. So sigma and pi, दो नए orbitals बन गए. These orbitals have different shapes and their energy levels are lower than individual p or individual s, जिसकी वजह से ये ज़्यादा stable होते हैं, जिसकी वजह से electrons ऐसे share करना prefer करते हैं. So we will explore this further in the chapter on bonding. But right now, what you have to understand is that the end game of any atom is to get maximum stability by lowering the energy that it needs to give to its electrons. And we'll try to achieve it by any means necessary. So right now, we saw that individual atoms have these subshells. And within the subshells, they don't shy away from bringing one electron from one higher level to lower level if they can, like copper and chromium. Then, not only that, if they have individual electrons and they want to make the cloud symmetric and they want to oppose their spin pair repulsion and gain more stability, in one word, they try to overlap these orbitals with other atoms and they form new orbitals which are lower in energy and more spaced around. क्योंकि जितना कॉम्पैक्ट होगा ना उतना ज्यादा इलेक्ट्रॉन एक दूसरे को रिपेल करेंगे, उतना ज्यादा उसको रिटेन करने पे एनर्जी भी लगेगी. जितना ज्यादा उसको इंडिपेंडेंस मिलेगी, जितना ज्यादा उसके पास एरिया ज्यादा होगा, उतना ज्यादा वो कर सकता है, उतना ज्यादा वो स्टेबल रहेगा. ठीक है. So they form two kinds of new orbitals with S and P. One is sigma, which is always the first bond formed between any two atoms. And then there is pi, which is always the second or third bond formed between any two atoms. So just remember, they want maximum independence and minimum repulsion. And that is what more stability is. We will explore this further. Tomorrow we'll talk about a very important theory, which is called VSEPR theory, which is pretty interesting. And okay, we'll build upon this idea.